So we have an experiment this week, right? Friday at 1. It's uniform circular motion. It's actually going to be that apparatus. Remember when there was that upright and I twirled this thing and this mass went around? Yeah, that's the apparatus that we use. Okay, so this is just chapter 6. The second chapter on Newton's laws, or force and motion. And there's a couple of conceptual questions here. The first one is number 5. You're pressing an apple crate or whatever against a wall so hard, a vertical wall, that pressing so hard so that it doesn't slip down. Okay? And this is, this is possible. And in fact, rock climbers take advantage of this. Anybody do any rock climbing? Yeah. So you there's a nice picture in one of the problems here. We're not going to do it. Yeah, number 79. The picture kind of says it all. I think it's 70. Yeah. So what's going on here? They ask several questions here. So we're exerting some force here. It's not moving. So the force diagram looks like this. There's this applied force. The force is on the mass, right? There's an applied force F here. There's a normal force due to the wall. There's a weight. And then there's a static frictional force. And am I going to set this equal to mu times the normal force? No, remember, the static frictional force can exist in a range of values. Just think of it as a simple demo, exerting a force on something, right? I'm exerting a force here. The static frictional force exists in a range. It's the maximum value. The maximum magnitude is the normal force times the coefficient of static friction. So we just want to call this the static frictional force here. So I think they ask what direction. It obviously points up. It has to balance the weight here. Now, they ask what happens if we increase the applied force? And it's simplest here to imagine doubling the applied force, just as a special case. It's not going to matter. So if we double F, what has to happen to N? The normal force has to double. What happens to these two forces? Yeah, nothing happened. The answer is nothing. And you would have gotten that wrong if you set this equal to mu times the normal force. Okay? So they stay the same. However, what happens to the maximum static frictional force? It's going to double. So this is why, if I want to I'm doing this, right? So if I don't exert enough force, it's going to slip, right? And it's because when I reduce the applied force, I'm reducing the normal force, and the maximum static frictional force is going to be reduced. So as I ease up on the force that I apply here, eventually it's going to slip. Right when it slips, that's when the frictional force has maxed out. It's equal to mu times the normal force. Any questions about that one? Yeah.
You times the normal force?
Oh, did I make a mistake? I'm sorry.
You said that's when it begins to slip. That's when mu is equal to the normal force.
Oh, sorry, that's when the static frictional force has maxed out, and it's mu times the normal force. Sorry, I might have made a mistake. Yeah. It's Monday morning, right?
Yeah.
Whenever it begins to slip, does that static force, does that change to kinetic force?
Yeah, it all of a sudden drops very abruptly. Once it just starts to slip. And we'll see that in another problem here. I'll show that to you on a graph. That's right. So it will not move with constant velocity, it will accelerate. Because now all of a sudden, the net force is not, just before it starts to slip, the net force is 0. Just as it starts to slip, this drops abruptly because it becomes kinetic friction, and we'll have acceleration. And we saw a demonstration of that, of the block on the table being driven by hanging weight. Any other questions? So there's, I think, another conceptual question here. Again, friction. Oh yeah, so this is what the graph we're going to see here. So here's the situation. We've got a block that's resting on an inclined plane, right? And when there's no applied force, it's just resting there. So what's going on there? Well, the static friction is keeping it from accelerating down the block, okay? Now that's not always the case, but in this case, if you make this angle too big, it's going to slip. We demonstrated that, and it's obvious. Remember that? The plank and the block, that box with the weights in it. Okay, so what's happening in this question here is that the force starts off from 0 and is gradually increased, this applied force along there. So the force diagram looks like this. And to make this clear here, maybe it's better to separate those two forces to make it, you don't have to do this, but I think it can help. So there's two forces that are together preventing the block from sliding down the ramp here. There's the applied force and the static frictional force. So what happens if we start with the applied force equal to 0? What happens to the static frictional force? Well, we have equilibrium here, okay? Until it slips, we've got equilibrium. So from the force diagram here, I can write that there has to be a balance between this force, the sum of these two forces, and this component of the weight, the gravitational force, along the incline. So they're going to be equal to 0. They're going to balance each other. And similarly, we have to have a balance here because there's no acceleration perpendicular to the incline. So we have to have this. The normal force has to be that. So what does the static frictional, just qualitatively, what does the static frictional force do as I start big F, the applied force from 0, and I start to increase it here? It's going to have to go down, right? Because this is a constant. As I increase this is going to have to go down. And eventually, what's it going to equal? If I keep slowly increasing F, what does it have to equal?
0.
0. At that point, we have a problem that's equivalent to a frictionless incline. If there's no friction here, you know that you're going to have to exert a force to keep it from moving, and that's the force you're going to have to exert. It's in that case, it becomes a special problem of no friction. So Fs will actually go through 0. We can plot sketch the magnitude of the frictional force here. It starts off with F being 0. It has to be mg sine theta, with the applied force being 0. And then as I increase the applied force here, it's going to be reduced. And eventually, when the applied force is mg sine theta, that's going to be 0. And then if I keep increasing it, what happens? Now it goes the other way. Okay? So as I go beyond this, now to have this equilibrium here, once this becomes greater than mg sine theta, the frictional force will be pointing in the other direction. It's a reactive force, and it can do that, yeah?
But if you're increasing F to the point where it's now countering static force, wouldn't it just be if you're not, are you assuming you're looking for equilibrium there?
Yes, okay. Yes. We haven't gotten to what you're going to ask. We haven't gotten there yet. So we've gotten here, right? Everybody understands that. We can keep going. Now it goes negative here. So I'm plotting this is the signed quantity here, where positive is that way and negative is this way. If I keep increasing that force, and this is what Eric's wondering about, what's going to have to eventually happen? Eventually it's going to slip and it's going to go up the incline. You know it. It has to be. And at that point, what happens? What's happened to the frictional force at that point? The static friction. It's maxed out. It's a maximum in the negative direction. Its magnitude is a maximum. So that's going to happen. That's going to happen right here. Okay, at some point it's going to happen here. And when it maxes out, we know that it's mu times the normal force. So that's how I came up with this right here. So we know it's going to max out. If you increase the applied force the slightest amount beyond that value, what happens? If I increase it slightly beyond this value here, it's going to break the static friction is going to break, and it will start to move up the incline, and it will accelerate because the friction abruptly drops to kinetic friction, which has less of a coefficient than static friction. So at this point right here, this now becomes kinetic friction, and it has a magnitude that's in general less than the magnitude of static friction. Yeah, maybe these are, these, I think these conceptual questions are good. And you're, of course, free to look at other ones. You know, you can do this on your own. And you can always come by. I told you there's a long history of these interesting conceptual questions. Remember I told you that? It goes way back. So I studied from when I was an undergraduate. It was the second edition. Yeah, the first edition, I think, came out in like the 1960s or something like that. So there's this long tradition of having interesting conceptual questions. So you can always look at other ones and come by and talk to me. Was there a question? Yeah.
So this is all an ideal environment, correct? It's not real world that we're in here.
Remember Galileo? We want to make progress, right, in dealing with the real universe. So we have to idealize things, okay? We're always coming up with models, and we just make the models more and more realistic. You can never come up with a model that exactly reflects reality. There's always going to be something complicated going on. You just hope that it's negligible for what you're interested in. So this is real. This is including friction. This is realistic. You could do an experiment. You can take data and you could take data on this, and then you can compare it to the theory. And you're probably going to see differences because this is an approximation. You know, this as I told you, how we handle friction here is an approximation. In the real world, there are going to be non-uniformities along here. Right, so I don't know, what was your question?
That's, I guess conceptually I'm just having a tough time with you saying that friction goes to zero. I can understand if you said effectively zero, but in my mind there's always going to be some friction.
No, there has to be a point where it's going to go to exactly zero. If you want to find that experimentally, you're going to have to be very careful, okay? And there's going to be fluctuations. This is at some temperature. There's going to be building vibrations. But there has to be a point where this crosses here. If I've got a line here that's positive here and negative here, there's got to be a point where it's zero. And at that point, the applied force is balancing this component of the weight. Okay, any other questions? Okay, the next, these are the problems, I think. 10. So this is, I'm sure somebody's been able to repeat this, but if you look at the diagram there, this person in around 1915 was able to hold himself up by holding onto these rafters here, okay, these probably 2x4s. He was able to hold himself up. And when you're doing that, this thumb is exerting a force this way, right? So there's an applied force due to this thumb this way. There's a reactive normal force pointing this way, right? And similarly over here. And these forces are going to have the same magnitude. So I see a normal force here. I see an equal and opposite normal force there. They have to be the same because otherwise we'd have some acceleration. And we have the same thing over here. So if we call this this individual force right here, great, I forgot my water. If I call this normal force in here, do you see that there are 4 of these involved here? 1, 2, and then over here, 3, 4. So that's what I've drawn in the force diagram there. And this person was able to squeeze, was able to apply a big enough force here such that he was suspended. Right? So the force diagram looks like this. There's a weight. There are these 4 normal forces, a total of 4 for the total. This is the total person. We're adding it all together. There's a total of 4 here. And it was balanced by the frictional force. The minimum normal force, which is the minimum applied force, is going to be when the frictional force maxes out, when it's equal to mu times the normal force. And the total normal force here is 4 times what we're the individual normal force in here. So this is the force diagram when the person's barely holding himself up there. So this is the minimum force that the person has to exert by the thumb or the fingers or either hand. So our force diagram gives us this. There's no acceleration. And we're maxed out on the frictional force here. And that tells us what the force that the person needs to apply by the thumb or the fingers is. And it's about 62 pounds. It's a I've added a significant figure here. That's okay. 2, 3. I'm not going to worry about that. And some of you you're still overly concerned about significant figures, which is my fault. But I think you're, as long as, 2 or 3 here, it's okay, right? If you want to be careful, you would say 280, right, to 2 figures. If you want to be really careful, what do you have to do? You don't know that the 0, you would write it as 2.8 times 10 squared. Nobody does this, okay? Very, very few people do this. But anyway, it's quite a force. And you may not think this is that much, but we're talking about somebody's hand here. And the text tells you if you don't think it's impressive, just try to do it. Maybe some of you can do it. I don't know.
Well, what sounds impressive is reading it is after he did it, then he started going hand to hand and doing it.
Yeah, he clearly built on this, okay? And, right, you can check that out. And he chinned him. I don't know if chinning's the right word here. He pulled himself up, I think, too. Yeah. So this is the minimum force that he has to exert by a thumb pushing this way, or the fingers. That's the minimum force for him to suspend himself, because we're given a certain coefficient of static friction here, right? It's 0.7. Questions? Somebody had a question there? Okay, so a drag question. And our interest here is, I think it's pretty much completely our application. What we're interested here at this level is terminal velocity, right? And it comes about due to the whole fact that the drag force, the force of a fluid on an object moving in the fluid due to viscosity, is highly velocity dependent, and that gives rise to terminal velocity. So what we're focusing on here is terminal velocity. There's a lot more to fluid mechanics than that, okay? So in 37 here, excuse me, we've got a jet flying at a relatively high altitude with a relatively high speed, and we've got another aircraft a lower speed at a lower elevation, and we want to compare the drag forces, assuming they both have the same size and shape. So they're going to have the same cross-sectional area. Here's the drag force. This is actually a definition. This is how the drag coefficient is defined, this dimensionless quantity here. And the drag coefficient, remember, depends upon the shape and depends upon the velocity. However, in this problem, what are we going to assume about the velocity dependence of the drag coefficient? I don't know if they carefully state it here, but it happens a lot in practical problems that you're in a regime where the drag coefficient is independent of velocity. All right, remember that? Yeah. So we're going to assume that the drag coefficients, it depends upon the areas are going to be the same here. But there, I didn't say anything about this in here. But in general, this will depend upon the velocity. But here we're assumed that they're, which is it's fortunate that often it's a decent approximation. So let's write down, what do we know about the jet? Well, it's the drag coefficient times 1/2 the density of the fluid, which is less than the density, because it's at higher altitude. The speed of the jet squared in the cross-sectional area. We can write down for the propeller plane, that's the one that's flying at the lower altitude. We can write down a similar thing, different density, different speed, but the same area. And it's very natural here to take the ratio, and they actually instruct you to do that because these common quantities will cancel out. And here's what we get for the ratio. And now you see here that, you know, what's going to win out? The jet is moving faster, but the density is less. So there are competing effects here. And qualitatively, you wouldn't know which one's going to win out. Now, it does depend upon the square of the speed. So that makes this, you know, more effective. But until you plug the numbers in for this problem, you don't know. But we're given those numbers, and you plug them in, and you find that it's roughly twice. So even though the density is less, which is going to cause a reduction in the drag force, the speed is, it beats it out, okay? Oh, and we're given the fact that the propeller is moving half the speed of the jet. Okay, any questions? We'll do another terminal velocity problem later on. Any questions? Oh, I guess. I guess not. So that's it. Oh, it's included, excuse me, yes, it's included in the next problem. Okay. So, we've got a skier going down a slope, constant slope. We're just going to do part A here. And what's driving the person is, of course, this component of gravity here, similar to this. There's going to be a static friction, there's a kinetic frictional force that's impeding the motion, and also a drag. Okay, now, because of that drag, because there's air drag, eventually the person's going to reach a terminal velocity, because that, as the person, there's going to be acceleration here in the beginning. And the speed will just keep increasing. That means the drag force is going to keep increasing. So eventually it has to be, you're going to reach, assuming you don't hit the bottom here or something like that, eventually terminal velocity has to be reached because the drag force is going up with the velocity. So the question is, what is that terminal velocity? So we draw a careful, maybe not real careful, maybe I should have done this to make it clear, but careful force diagram here. We have the weight down. We result the motion's this way, so we're going to immediately get rid of this and represent it as its two components. This driving force here, and then this perpendicular component, which is going to be balanced by the normal force. And the impeding forces here, going in the opposite direction, is a kinetic frictional force, which is just the coefficient of kinetic friction times the normal force. So it's going to be given by this, and then there's a drag force. When terminal velocity is reached, what is the relationship between these two, the downward force and the net upward force? They're going to balance. Terminal velocity is no acceleration. Newton's second law tells us that the force has to be zero. So we write the variable theta. And the student increases the angle here until the mass just begins to slip. We did that. And even if you didn't see it or don't remember it or you weren't here, I think everyone was probably here, you can easily imagine this, right? If I have something resting on here, you know that eventually it's got to slip. So it slips at a certain angle. And if we measure that angle, we can actually calculate the coefficient of static friction. Because just when it slips, the static frictional force acting in this direction will be maxed out, just when it slips. So again, here's our force diagram, and we're now specifying that this is right at slipping here. So I've maxed it out, the magnitude here. It's mu s, coefficient of static friction, times the normal force. The normal force has to be balanced by this component of the weight. So these two forces, just prior to slipping, or when there is no slipping, these have to balance. Just prior to slipping, this will be maxed out. So this is the equation we get. We balance those out for the maximum static frictional force. The m and g cancel, and we can solve, and we get this. And this is in the lecture notes. The coefficient of static friction can be determined in this way, and it's simply the tangent of the angle. Remember, the coefficient of static friction is dimensionless. So as you can see here, so this is fine. The fact that this is dimensionless has to be dimensionless, in fact. So we get a number with tangent of 30 degrees. Now, once slipping occurs, and I pointed this out in the demo. I don't know if you saw it or remember it, but it will actually, and we already talked about it earlier today, the mass will actually, not only does it move, but it accelerates down the plane. It does not move with constant velocity. It will only move with constant velocity in what case?
We tapped it and it was moving, it slowed down to like just beyond slipping.
So I'm sorry, so?
So it was when you did that example, you have a tap and it's kind of slowed down. Like
Yeah, now there I was lowering the angle. We're fixing, my question right now is a fixed angle. We fixed the angle. And suppose we did this and it just starts to slip. And suppose it moves down the ramp with constant velocity. What has to be true? What do you infer?
Coefficient of static friction is the same as kinetic friction.
Did everybody hear that? The coefficient of kinetic friction will be the same as the coefficient of static friction. But I don't know of a case where that's true. You can probably get close, but I think always or almost always the coefficient of kinetic friction is less than the coefficient of static friction. So because of that, once it starts to slip, now all of a sudden this mu s has become m mu k, which is less. We're not going to have this balance anymore. This is going to be greater, so it will accelerate. And in this problem, we're given information about the acceleration. So you get to go back to chapter whatever, early chapter here. Somebody's measured the time it takes to travel. Well, first of all, I think we're told that it's constant acceleration. In this case, what is this?
Yeah, 4 seconds at constant speed.
Yeah, so we're told this. And I know why the authors did that, okay? Because, again, our friction's just a model here. So what they're saying in a kind of subtle way is that the model is, we're going to assume the model works here. So they're just, the way that they're telling you that here is that the acceleration is constant. Again, if you did a careful experiment, I doubt if the acceleration will be constant. But typically it's close to being constant in some sense. So we're told the distance that it travels and the time it takes to travel, and that the acceleration is constant. And that it's released, and it's going to happen being released from rest, right? Because we're just at slipping here. So the acceleration here, once the static friction maxes out, here's our Newton's second law. We have this driving force down here. This is the impeding resistive force, and now it's the coefficient of kinetic friction. So we can solve for the coefficient of kinetic friction. We need to know the acceleration, however, but we can get that from the information they give us. This is very simple. You know this, the 1/2 AT squared. So we're given the distance and the time over which that distance is covered, assuming constant acceleration. And I screwed up here when I first did this. I didn't square the t, so I corrected it here. This needs to be squared. And I would have found that out if I'd put the units in here, right? So that's the downside of taking this shortcut here. If I had put the units in here, I would have found that, you know. But knowing me, I probably would have squared this, you know, squared the units, but not this. And so I would have thought everything was fine. So. But anyway, when you do it correctly, we get a value. And look at this value. Once you get this, what's the first thing you're going to do when you get this? You're going to compare it to the static frictional coefficient. And indeed, it's less. If you had gotten the same or greater, something would be screwy somewhere. Something's wrong. Okay, any question about that one? I don't know, we move fast today. So there's just one more. This is 84, and I told you we'd be doing something like this. So this is so I went to graduate school at UCLA, right? So every once in a while we'd get a phone call from Hollywood or you know, from filmmakers, and so they would have some question, you know. They'd want like a quick answer. And then they start pumping you for ideas. You know, I remember I was on the phone once with some guy for like a really long time, at least a half an hour. And so we were just coming up with ideas and all that. I was thinking, oh, this is great, you know. And then it was over, you know, and I wasn't in the credits. I never made any money. But they do, as you know, they do hire consultants, right? So technical people, you know, engineers, scientists, mathematicians, and often to do calculations, to do estimates. And sometimes this is for special effects things where, you know, it's dangerous. Somebody could get injured or killed, right? So it's a serious business. Just all for your entertainment, okay? So anyway, here's an example of where you can use some physics to estimate. Okay, this is all an approximation, right? We're making assumptions here. A certain situation. The situation is a stunt car driver is coming down here and goes over a hump, and you've all seen this, where, and you know what's going to happen is if you're going fast enough, the car will become airborne here, right, and move in approximately a parabola, become a projectile, as we would say in physics, right? So the idea in this problem is, given these this radius of curvature right here, to find what speed that is. What's the speed? What's the minimum speed here for which is just going to start leaving the ramp? And again, we can make this qualitative argument. If the speed is slow, you know what's going to happen. It's just going to go up and stay in contact with the road. If the speed is very great, it's just going to take off, right? So somewhere in between there has to be this critical value where it just barely remains in contact with the road. What does that mean mathematically? What does that mean in our theory? Barely remains in contact.
Static force.
What?
You max out the static frictional force.
What's the key force here? The normal force goes to zero. Yeah, you're making it too complicated. You gotta, this is common. Students make life difficult for themselves. I see it all the time. You know, it's like you want to do that? You want to make life complicated? So forget friction, forget anything here, except for the fact that when it just barely remains in contact with the road, the normal force will be zero. All right. So at the top here, now there is an assumption here, I didn't write it down. We're going to assume that the speed is constant right around here. You could be driving at a constant speed, which is typically the case. Well, I don't know. You know, the tendency, once you start climbing this, if you're pushing down a constant amount on the gas pedal, you're going to slow up, right? And you're going to speed up here. But what happens right at the top? It'll be, the velocity will be a minimum. So as long as there's no rate of change of speed here, we have approximately uniform circular motion. In a little arc around here, we approximately have uniform circular motion. But if you're speeding up, or let's say you're slowing down here, then there's going to be not just a centripetal, there's going to have to be a centripetal force here because you're moving in this arc. There can be a tangential component to that. We're not going to deal with that here. So we want to assume that the easiest way to say it is that dv dt is equal to 0 here. There's no change in speed, which will naturally be the case if you're moving with constant speed, or if you're slowing up here and then speeding up here, you're going to be at a minimum there. So dv dt will be 0. We discussed this in lecture. Okay, so what do we know at the top? In general, there's a weight, there's a normal force, and Newton's second law tells us that the net force is the mass times the acceleration. For uniform circular motion, the acceleration is v squared over r. Now, I've chosen down as positive here, right? See the mg? And I think I told you a long time ago that we're always going to take up as positive. I was wrong. We've done this. This is not the first time we've done this. But I think at this point you can, you probably are okay with this. But you want to be careful. I was just talking to somebody, Eric?
This morning?
Yeah, I think it was you. I know I talked to you, but I'm trying to think if I talked to anybody else. And so long ago, I can't remember. So you want to be careful when you do this, okay? For example, clearly I'm taking this to be the positive direction. I don't want to then look at this and say, oh, the acceleration is negative, okay? I want to have a plus sign there. We're into huge problems if you don't respect that choice of the positive direction. So this is what we know, and what do we care about? We care about this critical case where the normal force just goes to 0. That's going to happen for a certain maximum critical speed or maximum speed. This is the maximum speed for which the car remains in contact with the road, just when the normal force goes to 0. And we can solve for this easily. The mass, independent of the mass, which often happens as we've discussed before, and we just get the square root of gr and we plug in the numbers and we get 111 miles per hour. It's moving. Okay, but that's one of the reasons. Let's see. Yeah, I'm actually surprised, I'm actually surprised because look at this, 250 meters. That doesn't seem like much of a radius, right? It seems almost, oh, that's the point. Right, sorry. So the reason this seems so big to us is because this is so big. And you can look at the math here, but just physically, you know that as you make this smaller and smaller, the person's going to have to be going faster and faster to leave. When it goes flat, what's the speed? What's the maximum speed? Infinite. Yeah, so you know that as this becomes so, the reason this is so big is because this is big. That radius of curvature there is large. Yeah.
I'm still not following why we're setting n equal to 0.
We're going after this critical case. There's all kinds of cases where this the mass can go like this, right? And stay in contact. There's also cases where it's just going to take and be ejected up here. What we're after is the critical, or sometimes called the crossover case. So if it's moving with low speed, it's going to remain in contact with the road, as you know. If it's moving with a very high speed, it's just going to depart. So what's the crossover case? As I increase the speed here, there's going to be a critical value of the speed for which it just barely remains in contact. And that's the essential, that's what's important, that's the essential step in this problem. It's in this really nice, simple looking statement right here. What's going to specify, because again, at low speeds, there's going to be a normal force. At high speeds, it won't even make it it'll depart before it gets there. So the case that we care about, as you increase the velocity, you want to know what it's going to take for this thing the maximum speed that you can go and still remain in contact in the road is just when the normal force goes to 0. If you exceed that, it's going to become a projectile for a little. If you exceed it a little bit, it'll become a projectile for a little bit. If you exceed it a lot, it'll become a lot, right? Does that help? No? You want to, we got a minute, you want to re-ask the question, or?
So, in every other problem you've done, I understand you've had normal force bounces out mass gravitational pull as it bounces, but the fact
Yeah,
is-
because we had no acceleration in that.
Which was no-
Oh, yeah,
So,
right.
and now
Okay,
we're gonna break
that's
down.
right. Very good. I'm sorry. Yeah. So what's supplying? Something has to supply the centripetal force here. We have uniform circular motion in this little arc right here. There's got to be a centripetal force. And it's due to gravity, but also the normal, in general, the normal force will play a role here. And what's important is we've got to have the net force being this, it has to be, the net force has to be the centripetal force here. And so the net force from here is going to be mg minus n.
So this time we're actually adding a vertical portion of it instead of just horizontal when it goes up the hill.
What's different about this problem is we've got, it's not straight, it's not a straight, it's curved. That's the big difference here. We have uniform circular motion along a little arc right there. So now, this is a good point, now we have to have a net force. I guess in all the problems we've done before, because there's been no acceleration perpendicular to the surface, the net force has to be 0. Not now. Now we have to have a net force because this is moving in a little arc of a circle.
We're getting used to saying N is mg because in all points, N minus mg has always been 0. And this is strictly horizontal problems with this one, since there's a vertical portion, it's got to be equal to something.
Yeah, it's curved. We don't have a flat surface. That's the bottom line here.
Okay.
So this is moving, you know, everything before has been a flat surface. And because there's no acceleration. Now because it's curved, we have acceleration perpendicular to the surface, and that's called centripetal acceleration.
So for your force diagram, I mean, how would you annotate your centripetal force then? I mean, is it, I mean, obviously,
It's the vector sum of these two.
so it's your mg plus your
So these are the yeah, I understand the problem here. These are the basic real physical forces. There's a weight and there's a normal force. And this combination, mg minus, the difference here has to be the centripetal force by Newton's second law. It's got to be equal to the mass times the acceleration, and the acceleration here is not 0. It's v squared over r. Yeah.
It's like a tension problem where you have something on the end of a string, we spin it around.
Oh, we did do that problem.
Right.
Yeah,
So we
right.
assume-
That was the whole. And I started off. Yeah, I forgot.
We assume
So-
that at some point at the top, the tension goes to 0,
So-
so that way it departs.
Yeah. This is very similar to that problem we did in lecture, except instead of a normal force, we have a tension force. Thank you, Luke. Yeah. So it's very similar to that problem. So now, because the motion is curved here, there's going to be a centripetal force. The forces can't balance because you have acceleration. And we know the acceleration is v squared over r for uniform circular motion. Okay, good. Managed to use all the time. That's good. All right, so I'm going to send out a quiz, right?